Today I'm going to talk about the logistic function, and the main question that I want you to think throughout the video is there any way we can estimate the parameters of the logistic function? So here we go.
And I'm not gonna go into the details on how to derive this equation, but I'm gonna talk about the equation itself. So first, we have nt, and nt is going to be the number of cases on time t, so this is nt. And then we have a fraction that takes L over 1 plus e to the negative k times t minus t0. So let me walk you through each of the pieces that we have here. So L is the so-called carrying capacity, and carrying capacity is related to the total number of possible cases, so the maximum that we're going to have. Also, we have K, and K is the growth rate. So it's also known as the logistic growth rate, and this is telling us how fast is the function growing to the maximum carrying capacity. And then the inflection point, it's T0, which is the point where the curve, the logistic curve, is shifting from upward sloping, from an increasing slope to a decreasing slope. So let me show you the figure. So if we have nt on the vertical axis, and we have t on the horizontal axis, then the logistic function we know is looking very much like an S shape, where we're growing and then getting into a limit or carrying capacity. And then the parameters are k, which is telling us how fast this is growing. And also we have as parameters the inflection point, which is t0 right here. So the question is, how can we actually estimate those? So let us look at the equation one more time. So we have nt, we have L, we have K, and we have T0. Those are the main components of the equation. So the question is, what is given? So what we have as given first is the information that we know. So NT, we know NT. For every day, we know what is the number of cases that we have. The potential given parameter is L. L is given because we know the number of people in the country, or we know the number of people in the state. We know the amount of people in the world. So L is the maximum people that we think can get infected with the disease. So we know L. And then the parameters that we're interested in would be, of course, K, the growth rate, and then T0, the inflection point. All right? So we would like to get estimates of this. So we will call this K hat and T0 hat. Now, we can look at this part of the denominator, e to the negative k times t minus t0, and we can think of this in a little bit of a different way. We can separate this into pieces, e to the negative k times t, right? And then plus k times t0, right? K times t0. And we know that this is the same as saying e to the negative k t times t times e to the negative, e to the positive k times t0, right? And e to the k times t0 is just a constant that is not changing with time, so we can call this c a constant. So the whole expression in the denominator, e to the negative k times t minus t0, is just nothing but e to the negative k t times a constant c. Okay, so if that is the case, if we're looking at this equation using the second expression, where we are using c times e negative k times t, then the parameters in this particular case would be k hat and then also z. Those are the parameters that we're interested in. All right. So we observe NT, we know that. We know L somehow. This is something that I'll say let's assume we know L. And now the question is, we have the equation. Can we somehow get a linear relationship of the number of cases in terms of the parameters? So I'm gonna ask you that. Is there in any way we can actually get a linear relationship between the number of cases and the number of maximum capacity and the parameters k and t? Sorry, k and z.